the table 8-1. 5. Set the upper control limit and the lower control limit at and positive negative 3 estimated respectively. 6. Plot the sample statistics on the chart in chronological order. Note that in step 4, we estimate the standard deviation of the samples rather than calculate it directly. This is because we can invoke the use of the normal distribution, so the factors for the estimation are tabulated. Examples table in 8-1. The top half shows the formulas and the factors used in calculating the control limits for our four main types of chart. Note that the x is the sample mean, x the mean of the sample mean, the grand mean. R is the mean of the sample ranges, C is the mean of the sample counts, and P is the mean of the sample defective proportions. This is a table 8-2, tabulated factors for control chart calculations. The N, the samples is the N samples, factor A2, factor D4, and the factor D3. For control charts by variables, the factors A2, D3, and D4 are based on the sample size and are tabulated in table 8-2. These factors are multipliers that allow us to use the range to approximate the standard deviation of the process. This makes for quicker calculations, especially when you have a production worker updating the chart in the production floor. For control charts by attributes, we typically work with counts of or fraction defective, while counts are Poisson distributed and fraction defective follows a binomial distribution. We can invoke the CLT and use the normal distribution to estimate the mean and the standard deviation of both distributions. Both statistics can be calculated by knowing only the average percent defective or the average count. That makes it easy to develop either a P or C chart. When controlling by attributes, we only need to consider one chart to look for assignable causes. The statistical process control illustrations. Suppose you are responsible for an operation that cans beans. The cans are labeled not with for a net with 14 ounces. Indeed, an overall process average of 16 ounces have been found by taking many samples in which each sample contained 5 cans. The average range of the process has been 0.5 ounce. From this narrative, we know that the X is 16.0, R is 0.25, and N is 5.0. Consulting the table of factors for N is 5. Consulting the table of factors for N equals 5, we find that A2 is equals 0.58, D4 is 0.00, and D3 is 2.11. With a center line of 12, the control limits for the X chart are as follows. UCLX equals 16 plus 0.58 times 0.25 equals 16.14 ounces. LCLX equals 16 minus 0.58 times 0.25 equals 15.86 ounces. Accordingly, here are the control limits for the R chart. UCLR in 0.25 times 0 equals 0. LCLR equals 0.25 times 2.11 is 0.53. With a center line of 0.25, note in this example that the R chart is not symmetrical. That is because negative values of a range are impossible. So the normal distribution is truncated at R equals 0. Half of the probability density is still below the center line, although it would look skewed if you draw it. To look at another illustration where the normal distribution is truncated at 0, we will use an example of control by attributes. Say you are the owner of the landscaping company. You send out multiple crews each day to mow, edge, and blow clippings for your clients' yards. Since you cannot directly supervise each crew, you have implemented a random sampling approach to Evaluate the quality of service your company provides. When you inspect a job, there are a number of possible defects, such as an old patch of grass, also known as a mohawk, sloping agent along the walkways, and residual clippings left in the street. Of course, each yard can have multiple defects. Over the past 2 years, you have determined that the average is 2.4, so the UCL for that C chart is 7, and the LCL for that C chart is 0. So this is the figure 8-4A, sample of a statistical control chart. So in the past month, you have inspected 23 jobs and calculated and plotted the results presented in figure 8-4A and 8-4B. At first glance, the interpretation of this control chart may be confusing because the center line is not halfway between the UCL and the LCL. To clarify, lines have been added to represent 1 and 2 standard deviation above the mean, or the C. 3 standard deviations above the mean is the UCL. Examining the chart for an improbable point, you apply our rules of thumb. Is there one point outside of 3 standard deviations on either side of the center line? No. Are there 2 successive points between the second, or the C equals 5.5 and third deviation is C equals 7.1 above the center line? No. However, if you look below the center line, you see two counts of 0 in a row. That is not really improbable because 2 standard deviation below the center line would be 2.0 to 3.1. So there is more probability density below 0 than just the difference between the second and third deviation. Practically speaking, having 2 samples in a row and no defects is a good thing anyway. Are there 5 successively increasing or decreasing points in a row? No. Are there 7 successive points that are all above mean or above or below the shock or mean? No. But if the next sample has 3 or more defects, that could indicate there is probably a shift, a higher number of defects per sample than you would expect with C equals 2.4, since the previous 6 points are above the mean 3, 6, 5, 4, 5, 4. Another point to consider when using a C chart is that defect counts are integer numbers, so even though the calculated UCL equals 7.1, in practice it would be 7. You round to the nearest non-negative integer value. In the last section of this chapter, we will examine additional illustrations to practice your skill in creating and interpreting SPC charts. First, we need to examine one other aspect of interpreting control chart to ensure process quality. The process may be under control, but it is capable of producing the desired level of quality. Tables 8-4b, the sample of C chart. Process capability. A common misperception is that control limits are the same thing as specifications. Au contrary, specifications represents what you want the process to do. Control limits represents what the process can do. Specification limits, also called tolerances, are extrinsic, set outside the process. Control limits are intrinsic to or part of the process. Why is this important? Because you want to know if your process is capable of meeting specifications, especially if those specs came from a customer or the government. As in the case of NetWit claims on packaging, there are 4 possible scenarios when comparing upper specifications limit or USLs and lower specification limits LSLs with upper and lower control limits. The USL and LSL are outside of both the UCL and LCL, which means your process is capable of operating within tolerances. Second, the USL and LSL are inside both the UCL and the LCL, demonstrating the tolerances are narrower than the process can reliably produce when under control. The USL is less than the UCL and the LSL is greater than the LCL. This means if the process is in control, it is likely to produce values greater than the upper specification. For last is the USL is greater than the UCL and the LSL is less than the LCL. This indicates that you will have trouble meeting the lower specification. This is the figure 8-5, the sample scenarios of LSL, USL, LSL, USL from the 1, 2, 3, 4. They capable and meeting specifications, not capable, 3 capable and not meeting specification, last is not capable. Both scenarios 3 and 4 might be correctable by recentering the process. These scenarios are illustrated in figure 8-5. Think of USL, LSL, and as the allowable spread and the UCL, LCL as the actual spread. Conceptually, if your process is not capable of meeting specifications, you can recenter it and or make changes to reduce process variability. A fun animation of changing this process is available at this link. The http elsmar.com. Mathematically, we use indices to indicate process capability, where min is the lowest value or the minimum in the minimum functions brackets. The CP equals USL minus LSL times 6 CPT equals min USL 3 pa and pa in LSL and 3. This looks daunting, but it really simple arithmetic. I will spare you another poem though, since process parameters are typically unknown. We estimate that U equals X and equals A2 times R times 3 when control limits are positive negative 3, and we are using control charts for variable and is typical when evaluating process capability. When CP and CP key is greater than 1.0, the process is capable of meeting the allowable spread, as in scenario 1. Conversely, scenario 2 occurs if CP1 but CP key 1, that indicates the process should be recentered, as in scenarios 3 and 4. Statistical thinking is an important part of managing for results, although some managers shy away from statistics. 5. As you can see though, while the theoretical foundation is profound, the actual calculation and interpretation of statistics in process control are quite simple. It takes a small amount of quantitative analysis to uncover objective, verifiable, and then defensible and communicable insights that are critical to ensuring continuous process improvements. 6. SPC takes a proactive approach to ensure ensuring quality and elevating throughput by measuring during, not after the process. It informs decisions about process improvements and adjustments. It reduces waste in a process by identifying the presence of assignable causes. Perhaps most importantly, it enables you to determine whether you can satisfy your customers' requirements. Techniques: creating and interpreting control charts. The focus of this chapter has been on creating and interpreting control chart. So in this section, we will extend that work with some additional examples. As an operation manager, it is unlikely that you will be developing these charts yourself, but the practice of creating them enhances your statistical thinking. Example, the candy wrapping. The owner of homemade sweets knows it is important for each item produced to be individually wrapped before distribution. Each week, a random sample of 2,500 candies is taken, and the number of incorrectly wrapped candies is recorded. The results for a 12-week period are shown in Table 8-3. In this case, the quality characteristics interest is how well the candy is wrapped. This attribute can have just two possible values, correct and incorrect. So we know the best process control chart is a P chart. This is the Table 8-3. Data, for example, in candy wrapping, these are the sample numbers and the defects. The total of 147. The only real trick to this type of chart is to understand that the sample size is n is 2,500 and that we have n equals 12 samples. To calculate the average fraction defective, or P, we take the total number of defectives of 147 and divide by the total number of observations, which is n times n equals 2,500 times 12 equals 30,000. Then P equals 147,000 divided by 30,000 equals 0.0049 with a center line of 0.0049. The positive negative 3 control limits for the P chart are UCLP equals P plus 3 times square root of P 1 minus P divided by the n equals 0.0049 plus 3 square root of 0.0049 times 1 minus 0.0049 times 1 I divided by 2,500 equals 0.0091. LCLP equals P minus 3 times square root of P 1 minus P divided by n equals 0.0049 minus 3 square root of 0.0049 times 1 minus 0.0049 divided by 2,500 equals 0.0007. To determine whether the process is out of control, we need to calculate the value of pi for each individual sample. Simply the number defective divided by n, and then plot these results on the control chart. We need to calculate the value of pi for each individual, and then plot this result on the control chart. In doing so, we can see that sample 7 with P7 equals 24 divided by 2,500 equals 0.0096 is outside of the UCL of 0.0091. If this scenario were to occur in practice, the owner would likely ask someone on the management team to explore the circumstances when sampled. This is the summary of the whole chapter 8 of the process quality. So processes inherently have variability. Effective process control distinguishes between variability that is to be expected from variability that is triggered by one or more factors. Common causes of variation occur naturally in a process. Assignable causes result from specific and correctable causes. The theoretical foundation for a statistical process control is the normal distribution invoked by the central limit theorem. By measuring samples produced by the process, you can evaluate whether the process is in control by looking for statistical improbabilities. Control charts can be used for quality characteristics that are variables or attributes. Typically, control charts for variables use X and R charts based on statistics of the sample measures. The most common control charts for attributes are P charts for percent defective, and C chart for counts of defects. Implementation considerations for SPC include what quality characteristics to measure, what sampling plan to use, and what risk level to assume. Establishing initial control chart is a trial and error process until the process is determined to be in control. Creating SPC chart starts with the sample statistics. The mean of the statistics is the center line of the chart. The upper and the lower control limits are typically set at negative positive 3. That is our estimate of positive negative 3 respectively. Then the data are plotted in chronological order. To analyze the chart, we look for statistical improbabilities. A process's capability to meet specifications is determined by comparing its allowable variance to its actual variance. By calculating capability indexes CP and CPK, we can determine whether the process is capable and centered. Thank you.